Hello, everyone. Nice to see you again.
Good morning, Professor.
Hi.
Excuse me, Professor, can I ask a question regarding the long coupler? I've sent you an email. There was a problem with one of the problems where we have to find the volume. And if I insert the certain value of volume, long coupler says that I have to put more or less digits.
Yeah, I believe you need to specify this, then the problem, and contact the long coupler administrator with technical issues of long coupler. He is the expert to address these questions. Do you know his email?
No.
So you can check in this manual. There is a section, manual document. There is a section where it's mentioned about long coupler, and there is his email. Wait a second, I will double check it, and maybe I can send it in the chat. So again, I actually do it every time, but apparently you missed that part. So I will send it, share with you, so you have his contacts.
Okay, thank you.
No problems. 1 second. Oh. So, yeah, take a look here. So with all questions related to long coupler, we have long coupler like administrator. And this is Azamat Orazbayev. This is his email. Okay, guys. So I guess everyone who wanted to join is already with us. I would like to highlight that okay, so yeah, sure. In manual was written to use in general 3 significant figures and follow the manual with this. So homework in long coupler. Keep in mind that this week is training. You need to learn. You don't need to solve all problems. Of course, we encourage you to solve all problems and even more, but that really not going to be evaluated. The main purpose of this assignment is to give you a chance to practice with long coupler, that you know the technical aspects of this online platform. And starting from next week you will get assignments. Again, for next week, it will be, I guess, either late Sunday or Monday morning. You will get assigned problems for your homework during the 3rd week, and that will be your first homework assignment, which will be evaluated. So I got a bunch of questions from students regarding the uncertainties and standard deviations. So nevertheless, it's not really like physics related topic, most like statistical, but I believe that more general audience will benefit from discussing these questions, and we will start probably now talking about this uncertainties and everything what is related to them, so what can be relevant for you. Once we are done with this, I would like to come back to our topic, which we kind of finished yesterday. That was uniform circular motion. So I promised you that we will define next time more accurately from the mathematical point of view the direction of this angle of this radial acceleration for uniform circular motion. So last time we had more like physical approach to address this problem. We were considering the motion with vectors along this circle, and based on some features of geometry and like similar triangulars, we were able to derive equation for radial acceleration. However, today we will try to approach this question from purely like mathematical point of view, and you will see how the calculus can be very beneficial to get this answer. And I believe it's really nice to approach these problems from two different ways, and so you can feel the physics behind it and also get some mathematical description of this motion in more details. Okay, so let me try to change the screen and camera. Okay, so taking into account that we live in not ideal world, so some measuring equipment possess some error in measurement. Usually we when we measure something, the result is written like this. So let's say we have measurement m plus minus some uncertainty. U stands for uncertainty. So that could be like 50 kilograms plus minus 0.3 kilogram. So this is uncertainty, and that means that our measurement is not absolutely correct, and we get value within like accuracy of plus minus 0.3 kilograms. So then the next parameter which could be considered is so-called relative uncertainty or fractional uncertainty. So let's call it like this: relative uncertainty, or in other terms, fractional uncertainty. And this is equal to the absolute value of the ratio between uncertainty and measured value. Let's call it measured value here. So you see, this is uncertainty and this is measured value. If we take the ratio between them and like absolute value, then usually it's multiplied by 100%, because this is just relative parameter, so we can present it in percents. Next step is relative error or relative or fractional error. So relative error or fractional error. That is equal to the ratio between measured value minus expected value. So and this is divided by, so we have this difference, and this difference is divided by the expected value. So means expected value, it's something, for instance, you get some mass where it's written, I don't know, 80 grams, for instance. So this is expected value. Then you carry out the measurement, you get measured value, and then you can calculate relative error, which is measured value, which is, let's say, 75.5 grams minus expected value, 80 grams, divided by the expected value, 80. And yeah, this will be something around 0.056. Oh, no, will be 0.007. And since we multiply it by 100%, it will be like 0.7%. So this is the relative or fractional error. Okay, then let's move further and consider some other statistical parameters which we can define by processing our measured values. So one of very common is so-called average. Good. Let's call it AB. Let's call it like this. So this is average, or another word is to define this parameter is mean. So in this case, it's equal to the sum of all our measured values divided by the number of measurements. So quite standard definition. So we have sum of all values which we measured divided by number of measurements, we get the average, or oh yeah, you are right. Actually, you are right. Let's check it out. So 0.056, and this will be like 5.6%. Okay, thank you. Let's go first. So we have this average definition. Then with next parameter can be, which kind of very often is used, is it's called deviation. Yes, deviation. It's equal to some x value minus x average or mean. So this could be equal to some average value, and then if we have some measured parameter x, then we subtract mean or average value from this parameter, we get the deviation. Also, there is average deviation. Average deviation is the sum of deviations for all our measurements. It's like x1 minus x average plus absolute value plus x 2 minus x average plus xi minus x average. And this is divided by the number of measurements. Okay, so we define most important parameters, and now I guess we are ready to proceed further with defining what is standard deviation. Let's go to another slide. Oh, actually need to. Okay. So standard deviation. Okay. So let's assume that we did some number of measurements of some parameter. And we put here number of measurements with value x versus values x itself. And let's say we have like 5, 10, 20, oh sorry, 15, 15, 20, 25. And here we also on this axis we have let's put 5, 10, 15, 20. So this is number of measurements and this is the values of the parameter. Then let's say for 20 of our measurements gave us result which is equal to 15. Then a bit less, like 15 maybe, gave us 10, about 13 gave us 20, and then it decreases further when it goes further from the 15. So this is some distribution of our results of our measurements, and obviously that this n as a function of x is proportional to e as a function of x, which is probability. So you can also put on this axis probability. And you see that it looks like some bell-shaped curve. If we somehow summarize this result. So this is so-called normal or Gaussian distribution, and it's very common in nature. So this is very common distribution for different natural processes of which happen in our everyday life. And there is a special function which describes this, like Gaussian distribution, which is, we can write this probability as a function of this x is equal to, let's say, some constant multiply exponent minus x minus x average square divided by 2 sigma square. So this is a Gaussian distribution, and what does it mean? It gives us, so by the way, this sigma is standard deviation. So this equation gives us the distribution. So how we need to read it? Probability that in a particular measurement, so we have one given measurement. So the probability that in this one given measurement, the value of our measured parameter will be in the range from x to x plus delta x, some small change in x, will be equal to p as a function of x multiplied delta x. So what does it mean? It's just area, actually, under this curve. So let's say if we say, okay, if we do one measurement of this particular system, which is described by figure on this slide, what will be probability that our value which we measure will be between 5 and 10. So that is actually this area under the Gaussian distribution in this range. So obviously, if we ask another question, what will be probability for measured value between 15 and 20? So it will be here. And we see that this probability, this area, is larger than this one. So it's closer to the maximum of the Gaussian distribution. So let us draw this Gaussian distribution oh, good question, how standard deviation relates to the vectors like physics. I mean, it definitely depends, because every vector has or doesn't matter, every quantity, vector or scalar, you can define it with certain accuracy, and then you do this, you apply this measurements of different parameters. You need to measure time, velocity, you need to measure mass or acceleration. So every measurement provides you with certain uncertainty, and that need to be statistically analyzed. And finally, you need to show error bars with when you have some plot of one function as like some function versus independent variable. And then you need to show error bars within which range this measured parameter is correct. So definitely it relates, it's not, I would say this, what we are talking about, this, as I mentioned before, it's not physics for sure directly, but it relates to any aspect of science or human life. It's used in sociology for some statistical analysis, and also used in physics. So that is very general knowledge, which just everyone should be familiar with. Doesn't mean that you deal with this every day, but definitely this is relevant information to be aware of. That's why I decided that doesn't matter what major you are from, it is relevant for your field, and physics included. So let's continue further and maybe define some parameters of this Gaussian distribution. Let's draw another graphic. So we have x, e, x. Then we have this bell-shaped distribution. So at the maximum of this bell shape, we get the average value for our measured parameter like x. And what is interesting, that in the range minus 1 sigma plus 1 sigma, the probability of, so the area here, will be about 68%, that our measurement, some given measurement, will give us value within x average plus minus sigma from this equation. If we consider range of minus 2 sigma plus 2 sigma, it will be already something like 95%. So it's almost for sure you will get the measured value of our parameter x with some given measurement within the range x average plus minus 2 sigma. Another fundamental feature of this Gaussian distribution is that the integral from minus infinity to plus infinity of e x e x is always equal to unity. So it's like 100%. So what does it mean? That doesn't matter what we measure, what parameter x we measure, but this you cannot measure anything what is smaller than minus infinity and what is larger than minus infinity. That's why it doesn't matter what we measure. We will have a value which is in this range. And that's why probability of getting this value is equal to unity. So for sure, we will get something what is in between minus infinity and plus infinity. Okay, so now we described this Gaussian distribution, and let's see how with some experimental data, maybe when you have some measured parameter x, you can calculate this sigma as like standard deviation as an important parameter. So let's go to another slide. And for that, there is equation, which you may already seen. It's equal to square root of the ratio between the sum from I equal to 1 to n, which is number of measurements, of deviations of each measurement from the average value squared, divided by n minus 1. So this is the equation. We define what is deviation. So this is just measured value minus the area of this distribution, it's equal to unity. It gives you the 100% probability that you will get some number between minus and plus infinity. So this is equation with when you have n measured values of parameter x, sum all these n deviations from average value squared and divided by n minus 1. So the important question here is next step, which is projection of errors or uncertainty. Let's say if you have some function of independent variable x, and you know a standard deviation for this independent variable x. How do you get the standard deviation for the function itself? So for this case, we need to use the following equation, which is standard deviation of the function equal to the module, like absolute value of the derivative of this function over independent variable, multiply the standard deviation of independent variable. If that is also possible, you have a function with more than one variables. Let's say you have x and y. Then, and also you need you know standard deviation for independent variable x and standard deviation for independent variable y. Then the standard deviation of this complex function, I mean, a function of two independent variables, not complex function, will be equal to the square root of derivative of this function over x squared multiply sigma x squared plus the derivative of the same function but over other independent variable y square multiply sigma y square. So these are very general approaches to address basics of like error analysis, and I believe this is what definitely enough for you. If you want to dig into it, you're welcome, but it gets more and more complicated when you go further. But for like most everyday tasks, this level of understanding of these features will be enough. So I don't know how it will be for next assignments. I don't assign problems. There are other professors who check them and assign. But that's quite possible that there will be one of the requirements in the problem to calculate some average or get some standard deviation. So best to my knowledge, you got some problems based on these uncertainties and error standard deviation analysis in this assignment. Most likely in all like further assignments, this will be further considered, but not very often. So usually you don't deal with this very much later. More you deal more with physics laws and concepts. However, again, it depends on the problem. It can be required. So just be aware of these features. So office hours. Yeah, taking into account, we had a discussion with the head of department, and taking into account the flipped online class which we deliver now, all our lectures are kind of discussion with students. That's why you are welcome to prepare your questions. You can send me questions beforehand if you have some in between our meetings, maybe online. I can check. I don't promise that we will address all of them, but most relevant questions which represent interest for wider, like broader range of students, we will discuss during this online classes. And this is the opportunity for you to ask questions and get some answers. What is not,
Professor?
Yeah, so there's a question with problems. Oh yeah, so long kappa problems. This is assignment for your homework, which is the way how we're going to monitor your progress and evaluate you. So definitely not me, not either your recitation instructor will help you to solve problems from home assignments. That is your responsibility. However, you have specifically designed like recitation to solve problems, to learn how to solve problems. And this is the platform where you ask questions which are related maybe to problems which you get for homework in long kappa, or some ask to solve some problems which are similar to those, but definitely no one will help you to solve problems from your home assignments. That is your homework, which will be graded. However, all questions related to solving problems, this is a recitation. Okay, so now I guess we are done with the...
Excuse me, Professor.
Yes?
But is it possible for you to just show how standard deviation works on like any random problem similar to long kappa?
Yeah, that what is doing during what you are supposed to do during recitations.
So we need to ask for the problem clarification on recitations.
let's say you ask questions which are related to problems at homework. So it will not be exactly the homework problem, as I mentioned, but you ask questions which you don't understand from related to homework problem. And for some examples of solving, you ask this your homework instructor, not homework instructor, recitation instructor. And if you have some questions related to physics concepts and laws, you don't understand what physics is behind it, we can discuss these questions during our lectures. However, you structure your question regarding the physics problem, which the physics concept you don't understand, not specifically about problems. So we cannot discuss problem itself, but say that, well, okay, I don't understand how to go from angular velocity to linear velocity in uniform circular motion. Can you please explain? So this is an example what kind of questions we can discuss here. So it shouldn't be stated from your side that this is related to this specific problem. We discuss physics here, and please structure your questions in this regard with focus on physics concept and laws. And then, of course, if you see some problem in physics in your homework and you don't understand physics, you define this, look for physics in your problem, define what is not clear from physical point of view, from point of view of theory of physics, and then come to our online lecture or write me email, and we can, during online class, discuss these questions.
Okay, thank you for your clarification.
Yeah. Thank you for question. This is pretty much everything what I wanted to tell you about this error analysis. But now I would like to come back to physics finally. So, as we mentioned before, we consider now motion in two-dimensional space, and in particular, we consider uniform circular motion. So we have circle, and we have some radius vector, and this is our body which moves along this circuit with a linear velocity, which like its absolute value of linear velocity is constant. Okay, so as you may remember from our last online class and our last discussion, we considered how this velocity vector changes when we move from point 1 to, let's say, point 2. And then based on this change in the radius vector, like displacement of the particle, and change in the velocity vector, we were able to derive equations for radial acceleration, which is A equal to linear velocity, like absolute value, square divided by, by R. And that is equal to omega square divided by R. Omega square multiplied by R. So where omega is the linear, so V is a linear velocity and omega is angular velocity. So now let's go from the other point of view, as I mentioned, from the mathematical point of view. Let us consider what are projections of this radius vector on axis x and y. So we have here some angle theta, let's say, and we have one projection and another projection. So on x axis, this will be, let's call it Rx equal to absolute value of radius vector multiply cosine theta. And for Ry is equal to absolute value of radius vector multiply sinus theta. So this is clear, and then we can describe our radius vector as a sum of two vectors. It's unit vector I, which is arranged along this axis x multiply Rx plus j unit vector, which is in this direction of axis y multiply ry. So then we can write it in this form: absolute value of r multiply cosinus theta plus, oh no, sorry, I forgot I. So it's I multiply cosinus theta plus j multiply sinus theta. Okay, so that is clear. And now a question is, how do we consider a moving particle along this circle? So we need definitely to do something with this constant value of angle theta. We need to substitute this with something which depends on time. We know angular velocity, so that shows us how fast this body moves in terms of radians per second. And then that means if we multiply it by time, so we will show how this angle between the radius vector and axis x will change with time. So that's why in order to show to describe the uniform circular motion around the circle, we can write this Rx as, sorry, not x, it's as a function of time. No. So position of our body, which moves on circle as a function of time, will be, now I skip this absolute value, I just write r. So we know that this is absolute value of our radius vector, multiply I cosinus, instead of theta we put omega t, and plus j, sinus, instead of theta we put omega t. Okay, so this is equation which describes motion of uniform circular motion of a body in two-dimensional space. And you see how where it comes from, because we first define these projections, put them here, and then since it's obvious for everyone, we just substitute this constant angle theta with some function which depends on time. And this is omega angular velocity multiplied time. So if our time, for instance, will be t, capital T, which is period of one revolution, it will be this omega multiply T will be 2 pi. Means that we made 2 pi radian circle around, and that's 360 degrees. So we finished one revolution. And of course, it repeats further, again and again. So since we have defined radius vector as a function of time for this particular uniform circular motion, what we can do, oh, by the way, do you know why this particular equation describes uniform circular motion, but not some motion with not constant absolute value of the linear velocity? What should be different if we want to go from uniform circular motion to a circular motion with not constant linear velocity, absolute value? So you see that
omega. Omega.
Yeah, you are right. So this omega is constant here. So means that over time it doesn't change. It's only the product of omega constant omega 2 times shows us how we change the angle here. So we like rotate. Sorry for my drawing skills. I will probably improve them further. We'll see. So how we rotate this body around the circle. But since it doesn't depend on t, means we don't change angular velocity. If we don't change angular velocity, we don't change linear velocity, because there is a simple relationship between them. Linear velocity is equal angular velocity multiply r. R is constant, it's the radius of our circle, and constant angular velocity means our linear velocity is constant also. Okay, so now we have this equation, and let us go to acceleration. So we know that acceleration vector is equal to what? It's second derivative let's say it's derivative of dv over dt, also vector here, and this is equal to the second derivative of dr vector over dt squared. Okay, so means that we need to take second derivative of this function, which describes, like gives radius vector as a function of t, in order to get acceleration of this uniform circular motion. Good, let's maybe get somehow, cannot add more slides here, unfortunately. Let's come back here and delete this. So now we have this function, and we will take two derivatives over time. So how this function is defined? R as a function of t equal to r multiply I cosinus omega t plus j, so here is vector, sinus omega t. Okay, so let's take first derivative, dr is a function of time over dt. So keep in mind that, first of all, derivative of cosinus x is equal to minus sinus x, and derivative of sinus x is equal to cosinus x. So this is from tables of derivative, very basic functions. So ideally you should know it. If not, you should just take a look to this table. But keep in mind that we have a complex function here. So we have, so it depends, cosinus depends on omega t, and that's why in the argument of cosinus and sinus, we have linear function, which is omega t. So we need, when we take derivative, it's a derivative of the first function multiply then derivative of the second function, which is inside the first one. So this is also the property of derivatives. So it will be r, it's constant, so we just keep it outside. It will be I, then we have minus sinus omega t, and or maybe it will be better to write in another way. Sorry. Let's put this minus here, I. Then we have omega, which is derivative of the internal function, multiply sinus omega t. And then will be plus j vectors omega cosinus omega t. You see, we took derivative of cosine omega t. It will be omega multiply minus sinus omega t. Then we took derivative of sinus omega t, which is plus omega multiply cosines omega t. Okay, now we need to go further in order to get the second derivative, x dt squared, and this is equal to r minus I omega square, because we take again derivative of this sinus, so we get one more omega here, omega square, and it will be cosinus omega t plus j vector. Sorry, it's not plus because it will be minus. Minus because we take now derivative of cosinus, and it will give us minus sinus. So it will be omega square sinus omega t. Okay, what can we do with this equation? This will be, we can take out from the parentheses this omega square. So it will be r omega square multiply, and also we can take out this minus here. So we'll skip this minus in the parentheses. It will be I cosinus omega t vector plus j sinus omega t. And this actually r and these parentheses is nothing else as our radius vector. You see, we just need, yeah, we got the same expression. So this is equal to minus omega squared multiply r radius vector. And this result shows us, so we got, as you remember, for absolute value of radial acceleration, we got also the same equation. It's like v omega squared multiply r. But we were not sure in which direction it is aligned. So we made some we use some assumptions to tell that it's aligned along the radius vector r and in opposite direction. But here, from these two derivatives of the equation which describes uniform circular motion, we clearly see that it is directed to the opposite direction as radius vector r, and we need just to multiply as a coefficient with omega square, the angular square of angular velocity, and we get this radial acceleration, which every particle experiences while moving along during uniform circular motion. Okay, that was everything what I wanted to discuss with you today. I believe that these two approaches from physical and mathematical points of view are very helpful to have a more deep understanding of these features of uniform circular motion, which is very standard example and very common for also solving problems and also for applications in different fields. So thank you very much for attention. I wish you good weekend and take care. Hope to see all of you during our online class on Monday. Have a good evening. Bye. Okay. Bye-bye. Yes, on Monday. We will have class on Monday. Monday, Wednesday, Friday. That's every. Oh, it's holiday. Oh, sorry, I didn't know about that it's a holiday, but I will take a. Okay, thank you for letting me know. I will ask our head of department to clarify this and send you some message to let you know if that we don't have then lecture. I didn't know about the holiday. Thank you for letting me know. Bye. Have a good weekend.